Hey, good evening everybody, and welcome to this week 8 video, or part 3 on psychrometrics. What we're going to do today is we're going to dot some I's and cross some T's on some of the stuff we've been talking about on psychrometry as we close this chapter in our study of Thermo 2. So the goal for today's lecture is to really button up one of the important result of psychrometry, and if you've followed the solution that I've posted for week 8, you've noticed that there is quite a fair big use of that particular result, and it's not one that is jumps at you when you do the reading for psychrometrics, but it's one that really needs to be highlighted. And that goal is, how do we express the humidity ratio, which is omega? Remember, omega is defined as the mass of water vapor in a mixture to the mass of dry air in a mixture, the same mixture, and that's for a mixture of ideal moist air. You could say that moist air has a total mass of M sub mix, if you will, which is composed of both dry air and vapor. That's if we consider this mixture to be, say, in a closed volume, such as this. I've got this closed box, rigid box, of which it's made of some molecules of air on the inside. That's my system. The air is part of my system, and I've got some water blending with that, and that's what that would be. So MV for the water, MA in orange for the air inside that box. Okay. So how do we express this humidity ratio as a function of pressures? Okay, I'm leaving that purposely vague as there's multiple pressures involved there. But you see where this is going, right? We tend to measure the pressure of the air and of the vapor within the mixture more readily than the mass of vapor and the mass of air that we have in that mixture typically. Especially if we have not a closed system like I've got here, but an open system when we're in fact looking at rates of movement of moist air through it, like we had before. So our starting point here is I'm going to start with our psychrometrics video part 2 from last time, and which was an example that I was solving for you. And there's a series of equations in there that gets us almost to this result, this final result here, but I didn't need it in that form, so I stopped there. But in fact, now I want to really cast this final result in closed form, so it can be etched in your mind as you move forward, and don't have to really arrive all these different pieces every time you go. So going back to my closed volume right here, if I look at my mass of vapor, which is the water component of that ideal gas mixture, I can express it as a number of mole of vapor molecules inside that box times the molecular mass of the vapor inside that box, right? And that is equal to, as we saw in the last video, the partial pressure of the vapor in the mixture times the volume it occupies divided by the universal gas constant R sub u times the temperature of the mixture inside that box. This is what the number of moles of the vapor is inside that mixture, simply the ideal gas law, times the molecular mass of the vapor. Okay, and I called that last time equation 2. So I'm simply going to repeat it here. Similarly, without spelling out all of the components that we have here in that box, I'm going to give myself a little bit more room here, but it's exactly the same thing. For the air, the mass of air is simply going to be equal to the number of moles of air molecules times the molar mass of air, which again, using the ideal gas law, is going to be the partial pressure of air times the same volume divided by universal gas constant times temperature times again the molecular mass of air, and that's what I called in that previous video equation 3. So I'm keeping the same nomenclature. You got it right there. And so what we've got then, if I take equation 2 and 3 from that video and divide one by the other, then I've got the mass of the vapor divided by the mass of air, which, lo and behold, is the definition of humidity ratio, right? The this is a small m, small mass of air, and when I say mass of air, I don't mean mixture here. I mean dry air. The mixture, which is the total stuff that's coming in, I'm specifically calling that m sub mix. So this is the mass of air specifically. It's going to be equal to what I've got there in blue and in orange, dividing those things through. The volume, of course, is fixed. The universal gas constant is fixed. The temperature is the same in both cases. So all that's going to go away, and I'm going to end up with the partial pressure of the water vapor divided by the partial pressure of the air times the ratio of molecular mass of air and vapor, and that's what I call last time equation 4. And I just stopped there last time because I had everything I needed to finish my problem. But now I really want to cast this in nicer form. We don't need to carry out these these molecular mass as I've got here for no reason. So let's clean this up a little bit. The molecular mass of vapor is, that's what that is, right? Spell this out. Molecular mass of water vapor is simply the molecular mass of H2O, and H, if you recall, has a molecular mass of approximately 1 kilograms per kmol, whereas oxygen, atomic oxygen, is 16 kilograms per kmol. So all that gives us about 18 kilograms per kmol. Similarly, the molar mass of air, I'm going to let you look that up, although we could, by making a proper chemical composition argument for air, calculate this from scratch. I'm not going to bother doing that here. We'll simply jump straight to the result. So m sub air is molecular mass of air, and that's about 28.96 kilograms per kmol. Okay, so if you do m sub v over m sub air, m sub a, you're going to find that you get approximately 0.622. Okay, so that's an important ratio here in our analysis. Finally, if we apply Dalton's law to this mixture of ideal gases, what we've got is that the total pressure of that mixture, or P, I could call it P mixture, is equal to the partial pressure of the air in a mixture plus the partial pressure of the vapor in a mixture, which therefore means that the partial pressure of the air alone is equal to the total pressure, which is what you'd measure with a barometer if you were present there trying to quantify that mixture. minus the vapor pressure of the water in the mixture as well. Okay, so taking all this together and substituting it back into my equation 4, that means that what we've got is the humidity ratio is therefore equal to PV over P total minus PV times 0.622. So that's the final result that I was looking for here and that I want you to have handy as you move along. You saw me use that a lot in that last homework, and there's good reasons for that. It's just a fantastic tool here for moving through these psychrometrics problem a lot of the time, and I got from the comments from some of you that some of you are struggling with that, so I wanted to highlight that for you. And your book really goes through a similar derivation here, and its final result is expressed in equation 12.43, which I reference in my own solution. This is for Morin and Shapiro, 9th edition. Okay. Voila, that's the result I really wanted you to highlight and to remember. Now, as far as the partial pressure of the vapor itself is concerned, you can relate that to the relative humidity, which is also a quantity that's usually given to us in psychrometry. And the relationship there, pardon me, which you can recall from one of my previous videos here, the first one, part 1, where I define humidity itself, but the relative humidity, phi, is simply equal to the ratio of the partial pressure of the vapor in its actual state divided by the saturation pressure of the vapor at that same temperature, right? So that's the definition of relative humidity, and if it helps you, because it certainly helps me to think of it this way, you can look at it on a TS diagram where the saturation curve looks like that. Right, here's the saturation zone for a mixture at a given temperature, but I'm not there. I am on this isobar instead because I'm superheated, right? This would be my P sub V, and this would be P sat at that same temperature, T mix, right? And this is T mix right there. So, a quick review here. This is the distance between those two guys, or the ratio between PV and P sat. That's an indication of the relative humidity, and that's what I got here. But I'm highlighting that specifically so I can express the vapor pressure in terms of the relative humidity, and so that's going to be phi times P sat at the temperature of the mixture. Okay, voila. So now you see that I got the humidity ratio as a function of the vapor pressure, and the vapor pressure as a function of the relative humidity. So very often we have the relative humidity given and the temperature of the mixture given, and you can see how I can weave myself back up there and find the relative humidity immediately as a result of that. That's the key lesson here that we've got. How does this all work? Well, I thought I would take this opportunity here to go back to one of last week's homework problem to sort of explain how to solve that. So I copied it right here, problem 2 I chose. And that's a pretty involved problem, but a typical one for HVAC applications that involve dehumidification, right? So the process for dehumidifying moist air that's too hot and humid for our purposes, is to first cool it down for the purpose of dehumidifying it, meaning that we're going to extract some water content out of that moist air. And of course, what's going to come out of that process, once we start squeezing the water out of it, is that what's left with is much colder air, but that's saturated with 100% humidity. So to get ourselves away from that uncomfortable saturated air state is we're going to reheat it to our set point temperature that we want. So dump heat into that air, dry heat into that air, keeping the humidity ratio constant, keeping the total pressure constant. And so what we're going to end up with is a setup where at the exit to this process is that we have a target relative humidity for a comfort zone that's more suitable, and a target temperature that we wanted at the end of the process. So this is very comfortable air, for living compared to what we started off with going into this box here. So this is how a air conditioning unit that does its job well would work. And so on the psychrometrics chart, what that looks like as we split this overall process into 3 parts. The inlet at 1, this is where we start at. It has a certain dry bulb temperature, which is non-ideal, dB1. When we pass through the cooling coil, what we're doing is dropping the humidity because we're squeezing some water out of the air. And so therefore omega is going to drop. And at the same time, because we're cooling the air, the dry bulb temperature is going to drop. So that means a movement to the left and down based on where we started. So that's what's happening right there. We're going to the left and down. And that gives us our second state point right there. And finally, as we pass over the heating coil, what we're doing is we're not changing the humidity levels. So therefore, the humidity ratio at 2 is going to be the same as at what it is going to be at 3. But because we're raising the temperature, we're going to move straight to the right. And so our final dry bulb temperature is going to be higher than it was at 2 at the same humidity ratio and a different relative humidity, however, because we're moving away from that saturation zone, right? So that's the process that's taking place. It's 2 separate processes, and moving through what the problem requires us to determine now specifically is, well, what would be, given the parameters given, that intermediate temperature T2 for this particular setup. And this is the only thing I really want to talk about to you in this particular solution review. You've got the PDF, but it was a little bit difficult to follow, I think, if you were struggling with psychrometric to begin with. So that's why I want to go over it with you. So I'm going to specifically focus on figuring out what that intermediate temperature is. So first, let's go through our assumptions in our model. We are modeling moist air as a mixture of ideal gases constituting dry air, which is just air at 28.96 kg per kmol of molecular mass, and pure vapor, superheated vapor that behaves as an ideal gas in that mixture. So I can apply Dalton's law and everything else that we've talked about with respect to psychrometrics. We're going to assume that this entire process takes place at steady state. We're going to assume that there's no kinetic or potential energy effect that affects this problem. So therefore, my stored energy is simply the thermal energy that I have. And while there is no work done, of course, because I have an open system, I have some flow work that's happening to this fluid as it moves from 1 to 2 to 3. And so I'm going to grab that flow work, move it along with my thermal internal energy as before, and that's going to give me my enthalpy. That's what I'm dealing with, enthalpies. Since I'm modeling air as a perfect gas, I'm going to assume that my CP is constant. And I'm going to fix that temperature, that value of specific heat at the inlet point T1. But you're familiar enough with all this at this point to know that CP ain't going to change a whole lot. If somebody said, well, I'm going to pick the temperature at T3 to fix my CP, you'll find that you have a fraction of a 1% difference at the end of the day. Okay. Finally, when we're talking about, this is not something we're addressing right now, but when we're talking about volumetric flow rate of air here in a problem like this, it should be clear to you that unless specified that we're dealing with volumetric flow rate of mixture, then air implies dry air. And so that's what I ended up solving for in this particular problem. All right, so how do we go about to figure out the temperature at the intermediate point? And notice right off the bat, I'm going to start with that result that we proved above there. So I've got the mixture of ideal gases here with the conditions given. Okay, see what's happening here. Right. So I'm looking at the solution that I posted for that problem from last week, and I'm going through it. So what I'm going to do is first establish what these humidity ratios are, because the humidity ratio is going to be my direct indication of how much water gets squeezed out of the air, which is going to be given by this guy over here. We'll look at that over in a moment. But specifically, I look at what I know when, for a flow such as the one going through this dehumidifier, right? I don't know a whole lot of things. I know the state that I've measured, which is given to us, which is the relative humidity both at the inlet and at the outlet. I know the temperature both at the inlet and the outlet. That's T1 and T3, and Phi1 and Phi3. I also know, based on the data given, that the total pressure of the mixture remains constant throughout this entire process at 1 bar. Okay, so this is all I know in terms of raw data. In terms of model, what I do have is our old faithful conservation of energy, first law of thermodynamics, and conservation of mass. And I'm going to make judicious use of that here to get myself to T2 here. When you're looking at temperature, immediately in your mind's eye, you should see, okay, I'm going to need conservation of energy in there. And so I'm starting straight off with that. Let's look at the conservation of energy between state 1 and state 2. And given the assumptions that I made, no work done, etc. Basically, what I've got is this cooling coil is extracting stored energy from my flow between 1 and 2. So that means that the energy at 1 minus the energy at 2 is going to be equal to the amount of heat that's being taken out. Okay, so the energy at 1 is going to be the enthalpy of the air at 1 plus the enthalpy of the vapor at 1, the rate at which that's moving, minus the enthalpy at 2 for the air and the enthalpy of the vapor at 2. But now I've got less vapor. This mvap right there is not the same as this mvap there, right? The one on the left is at state 1, the one on the right is at state 2. So mvap2 is expected to be less than mvap1. Why? Because some of that mvap1 got transformed into liquid, which I'm going to call m.liq for liquid, and that is the water that's being extracted from the air at 2. So conservation of mass then on that stream would tell us that the mass of vapor initially, the mass flow rate of vapor initially is going to be equal to the mass flow rate of vapor after dehumidification plus the mass flow rate of liquid afterwards, right? So I think that follows directly. And so this is all the energies that are being considered between 1 and 2, and that's got to be equal to the rate at which heat is being extracted between 1 and 2. So that's what we got, and the problem did tell us how much that was. So this guy here was a given here. I think it was 11 ton that we were given for how much heat is being removed. Okay, so that's great. We've done all this, and we've substituted our CPT for the enthalpy of the air itself, and we've got some values here that we can look up. The enthalpy of the vapor at 1, we should have enough information to figure this out. We don't know the temperature at 2, so therefore we don't know the saturated enthalpy of the vapor at 2. But if we didn't know T2, we would know H sub G2. And similarly, we don't know the saturated liquid enthalpy at 2 because we don't know T2. But if we did know T2, we would. So we have one equation here. And in terms of unknowns here, what we don't know is the mass flow rate of dry air. It's one of the things the problem's asking us to do. We don't know T2. That's the key thing we're looking for. And we don't know the humidity at 2. So there's 3 things that we don't know. Of course, you could say, well, I don't know HF2, HG2, etc. But yeah, we do know it. If we find this guy here, we're going to know him off the bat. So I'm not going to list them for that. I think that follows straight. So 3 unknowns. Okay. Okay. So next, a little massaging with conservation of mass here, which I've already brought in, so we're good. Notice that the humidity ratio at 1 is defined as the mass flow rate of vapor at 1 divided by the mass flow rate of dry air at 1. And the humidity ratio at 2 is the same thing for state 2. So that therefore, the mass of liquid at 2, if I put the m dot vap2 on the left-hand side, is simply going to be the difference of these humidity ratios. And I showed you that result a little bit above there already. But it pays here to highlight that final result here, which is simply based on the definition of humidity ratio and conservation of mass. That's all that is. So part C, which was asking about the mass flow rate of liquid water, it's going to be kind of straightforward once I've figured out my state 2 fully, and I've determined what my mass flow rate of dry air is, and hopefully that's going to happen as we develop more equations here for M sub dA, right? So let's start to add some number here, and just so I don't get confused there with previous nomenclature that I've used, I'm going to call this equation A here for my first law application between 1 and 2. Okay. All right. What else do I know? I know that at state 2, my relative humidity is 100%, right? Because I'm saturated. The problem tells us that. So if I'm saturated, my relative humidity is 100%. And I know that the definition of relative humidity is the ratio between PV2 and the P saturation at T2. So if I'm at 100%, then my vapor pressure at 2 is simply the saturation pressure at T2. So that's going to be kind of nice. And based on the result that we've highlighted above, if I know that, I know my humidity ratio at 2, and that's going to be an important result too, right? Because it appears in a bunch of places as we saw above. So that's an important separate equation from the above. I'm going to call that equation B. And again here what I got is I got 2 unknowns, which are omega 2 and T2. So I'm making some progress here. I now have 2 equations and 3 unknowns, omega 2, T2, and m dot A. So moving right along. The rest is where some of you got tripped up, I think, is, well, how do I get my third equation in order to solve this without introducing a whole bunch of different variables? And what's key here is to observe that on the psychrometric representation of these processes here, and this is why making these sketches is so important, because it gives you a graphical interpretation of what's going on here, that between 2 and 3, the humidity ratio remains constant. So the mass of water vapor to the mass of dry air remains constant, which means that omega 2 is equal to omega 3. Why is that important? Well, because now I've already gone from 1 to 2. I don't know a whole lot about 2 except that it's saturated. And now I'm going to need to go from 2 to 3, and I know a lot about 3, right? I know the relative humidity, the temperature, the total pressure. So I'm going to use that to sort of go backwards from 3 back to 2, and that's what I'm about to do right here. So at 3, I know that the humidity ratio at 3 must be equal to our equation from above, where P3 is the total pressure, which remains constant throughout this whole thing, right? P3 is equal to P2 is equal to P1 is equal to P total, as I'm calling it over here. That's my 1 bar value, right? And since omega 2 is equal to omega 3, and I've got omega 3 there, I'm going to continue on with this line right here to illustrate that a little bit more clearly. That's got to be equal to omega 2, which itself is equal to 0.622 times PV2 divided by P tot minus PV2. So if you look at this expression right there, the only thing that are different are the PV3s and the PV2s. And by the form of this equation, I mean, you can just solve it for in terms of each of the variables here. It illustrates quite readily that PV2 must be equal to PV3. In other words, the partial pressure of the vapor at 2 must be equal to the partial pressure of the vapor at 3. And again, I know a lot of things about 3, right? I know its temperature, etc., and its relative humidity. So, right. So the statement that PV2 is equal to PV3 gives me this guy right there, which I'm going to call equation C. Okay. And finally, to evaluate PV3, I go back to the definition of relative humidity, and that gives me equation D right there, of the definition of relative humidity. So, okay, looking at this whole set of 4 equations now, right, I'm in very good shape. Equation D here is 1 equation and 1 unknown, because I know T3 and I know Phi3. Equation C is now 1 equation with 1 unknown also, because I've solved for PV3 in equation D, and my unknown is now T2, so I'm going to get T2 out of that guy. So your process, if you were doing this longhand, would be to start with D, substitute D into equation C, find equation C to get T2. Now you're done. You've got T2. You've answered part A of the problem at that point. You're done. So check part A. And then if you want to get further, you could take this T2 and substitute it back into equation B. And you would therefore get the humidity ratio at state 2. So you have this guy and this guy. And finally, you could take the humidity ratio at state 2 and the temperature at state 2 and substitute that back into equation A and solve for the mass flow rate of dry air, which is now your last unknown. Okay, so this is how you would do this longhand. And as you saw, I didn't bother to do this. I simply wrote an ease program that does this back substitution for me automatically and makes the process much less, slightly more rapid. And so voila, that's it. This is how these psychrometrics problems get done. And again, there's a lot of equation manipulation in this process at the end of the day, right? But it doesn't have to be if you're meticulous about the number of equations, the number of unknowns that you use in your process. When you write a well-defined set of equations in ease, you should be able to converge to the solution that way. The last step between 2 and 3 is another first law analysis that gives us the last unknown as a function of everything else that we know, right? We've fixed the state completely between 1, 2, and 3. Specifically between 2 and 3 is all we need for this first law analysis for the heat addition process, and so therefore we can solve for Q dot in, and ease did that for us down there. Okay, I just wanted to go over this solution process with you, because it's not necessarily completely obvious looking at the solution in PDF form straight off the bat. But hopefully this sort of demystifies the psychrometrics aspect a little bit for you. And to summarize everything, all that I did over here is applied first law between individual processes, 1 and 2 specifically, and then separately for part D between 2 and 3. Conservation of mass, which is always key to relate mass flow rate of various species between various parts of processes. And finally, to relate the humidity ratio to pressures that I have in the system to my new fangled model here, which is equation 12.43 in the Shapiro book. Okay, so hopefully you've enjoyed this, and this makes psychrometrics a little bit less mysterious for you and fairly straightforward. It's, again, another application of the same ideas that we've talked about all quarter long. Take care and have a great rest of your day. Bye-bye.